Okay, so for this one, I do want to just kind of do a walkthrough for this example problem. So we talked about conservation of angular momentum. Um, we've done problems where we have collisions, right? Where we have linear momentum and we have a collision, right? There are two objects, they run into each other, and either maybe they bounce off of each other and they go back in an opposite direction, or they run into each other and then they travel in the same direction with the same shared velocity. So we can apply the same concept to rotational momentum. In this case, this is just sort of an example of a rotational collision where we have two rotating objects and then they collide with each other and they stick, right? And then they rotate together. So with these collisions and with like our conservation of energy problems, we can pick time steps to look at, right? We can say like, okay, what is the momentum at point A and what is the momentum at point B? And those points are arbitrary. We can choose where we want to measure. Um, so we kind of have a luxury of looking at what happens before and after certain events. So yeah, so in this particular case, there's not a lot that's going on, right? That's very crazy, but we're looking at before and after the collision. So we can basically just say like, oh, well, we know how it starts, and then we want to know, uh, like after they run into each other, how it ends up. So um, we're assuming that the energy is conserved in this case. Like we don't have any energy um, that's inelastic that would be lost to like heat or anything like that. We're just going to conserve all of the energy from one step to the other. So we're going to conserve all of the rotational momentum. Okay, so we have this larger sprocket that's rotating, and then we have this smaller little piece that's rotating. And all that really happens is this guy is going to run into this guy, okay? So it's just pushing them both together, right? And then they're going to rotate together, okay? So notice that this force applied here, it's not going to generate any torque going through that axis as we're pushing them together. So we're not changing the angular momentum, okay? We're not adding any additional torque that would add any additional spin, right? So the reason why torque would change the angular momentum is like, say I'm applying a force and it's like along the direction of this rotation, that's going to add some change to the rotation, and that's going to change some component of that momentum because we're applying it right through that axis. If we think about how we model torque, like there's no distance away from the radius, right? So there's no torque. So from that previous problem, if some of it was confusing as to why pulling on that string in the center um, was uh, didn't cause any change in angular momentum, that's the reason why, right? If we apply a torque, we can change our angular momentum. Same thing as like if we apply a force in a direction of an object, we could change a linear momentum. That's why we can say that it's conserved because we're pushing right along that z-axis. Think about how we model torque, no torque, right? No distance away. So just for reference, those are f sine of theta, right? And then r is equal to 0. It's not any kind of distance away from that center where it's being applied, right? So not going to cause any rotation. Okay, cool. So, all right. So our conservation of angular momentum. So this would be similar as if we had two linear objects and they were sticking together, right? So we have, this is, right, the initial angular momentum of both of the objects. We can just add them together, right? 1 and 2. And then when we push them together, it's going to be the sum of the mass moment of inertias. And then we have a shared angular velocity for both of them. Okay. So we have conserved momentum and we can look at the relationship of that final angular velocity with those two objects smushed together. Okay. So yeah. So this collision is very similar to the completely inelastic collisions we've looked at before. So we are conserving angular momentum. So this is just kind of describing the same thing that I just kind of said here. So hopefully that one makes sense. I think that this concept is going to be kind of interesting to look at because we can use angular momentum in collisions. So I'm going to go ahead and stop this one and move on to the next problem. And we're going to kind of see a little bit of this in action. We're not going to have two stuck rotating objects, but we are going to take angular momentum and use a combination of angular and linear momentum to look at how things might change in a system.